second plenary talk of the day, which is an overview of challenges in additive manufacturing by Professor Trustee, Senior Professor and Chairman of Center of Product Design and Manufacturing ISpA. The session chair is Dr. P.S. Goel, former President INAE and already distinguished Professor ISR Headquarters. I request the session chair to kindly come to the dais, and I request Dr. A. Gopal Rao to kindly introduce the session chair.
Good evening, ladies and gentlemen. Professor P.S. Goel was the Director of ISRO Satellite Center, Secretary, Ministry of Earth Sciences from 2005 to 2008, and later Chairman of RSA DRDL, and Professor M.J.K. Menon, DRDO Chair. He was Vikram Sarabhai Chair Professor at ISRO. Currently, he is the Honorary Visiting Professor of NIAS. Professor Goel initiated research and development for satellite control systems. He has contributed significantly to the development of attitude control system, mission planning, and so on. He was appointed Secretary Department of Ocean Development, which he reorganized as Ministry of Earth Sciences, integrating ocean, atmospheric, and geological sciences. He was instrumental in setting up tsunami warning system in the country. Professor Goel was President of Indian National Academy of Engineering, member of National Security Advisory Board. He started the program Space for National Security at DRDO and was instrumental for the development of India's first elite satellite, Kautilya. He is a recipient of several awards for his outstanding contributions in the field of science and technology. Some of them which include Special Achievement Award for Aryabhatta, Harivom Ashram, Prerit, Vikram Sarabhai, Research Award in System Analysis and Management, Astronautical Society of India Award in the field of spacecraft and related technologies, Vasvik Research Award, and so on. Professor Goel is a Fellow of Indian Academy of Sciences, Bangalore, National Academy of Sciences, Allahabad, Indian National Science Academy, INSA, Institute of Electronics and Telecommunication Engineers, New Delhi, and Aeronautical Society of India, Bangalore, and so on. So we have a distinguished person to chairing the session now. I now hand over the session to Professor Goel. Thank you.
Thank you very much. Good evening to you all. We had a very exciting, interesting day today, starting first plenary from Dr. Patil, and happy to see that even though it's 6:30, but the hall is full, so it shows that it's a really interesting day. This is the last session of the debate, and we have a plenary 2, which is being given by Professor Amresh Chakravarti. He is currently professor as well as the chairman of the Center for Product Design and Manufacturing at the Institute of Science. He has multiple interests, various kinds of technologies, including design, synthesis, creativity, eco-design, sustainability. Also, he runs a program, sort of international workshop, once in 2 years on manufacturing. So he is sort of keeps the ecosystem of the manufacturing in a very bigger way. He is very active, and he is engaged in many international collaborations, including international projects on structure of creativity with the very foreign universities. Above all, very fine gentleman, down to earth, and if you can go anytime to his laboratory, he will show so much interest. So he is really a god player of manufacturing. So I invite Dr. Amresh Chakravarti for the plenary 2.
Okay, first of all, my sincere thanks to the organizers, Dr. Madhusudan Reddy, and the colleagues at National Academy of Engineering. It's a wonderful gathering. It's an honor and a privilege to present here. So, I will spend maybe 45 minutes or so on some challenges, the overview of challenges in additive manufacturing. It would be a very long talk. So I picked some of the challenges. So I just start with my department. It's called Department of Design and Manufacturing, earlier called Center for Product Design and Manufacturing. Started in 1998, we just celebrated our 25th anniversary. And I think we have a number of programs. We have a PhD program in design. We started the first in India. And Intake research program, just like any other departments at IISc. And Indes in product design and also an activity in smart manufacturing. We are also privileged to have a lot of top 2% most cited researchers as our faculty. About a quarter of our faculty are actually top 2% list of Stanford study. And also among some of the surveys, that international surveys, we count as one of the top design, most research intensive design schools in the world. In the manufacturing part, you get very impressive toughness characteristic. That will be much more stretched curve here. And finally, cost optimization that you could do using design for additive manufacturing. So let's look at an example that actually clarifies this importance. If you look at this, here, this study looked at 3 different scenarios, okay, and compared 3 different additive manufacturing scenarios and compared them with CNC machine part, same part, CNC machine, or part made using 3 different additive manufacturing scenarios. And what was done here was that, first one was that where this particular part was shape optimized. Okay. And the sintering that was used, the oven was used to its maximum capacity. So a large number of parts were sintered at the same time. So energy was not wasted. Second one was where the part was optimized for shape, but the oven was used with only one part, which is often the case. You do not really fill it up. And the third is where you did not optimize the part, it was a solid part, but sintering oven was operating at maximum capacity. So basically you have A and B, B and C, and C and A. And it's not surprising that, probably, that the first scenario where you have to optimize shape and also the oven was used to the full led to a very impressive performance compared to the others. In other words, when you optimize with DFM, minimum material consumption and support structure and then maximum production capacity, you have a very good combination to go for. So that's an important lesson for us and also paves the way for the importance of design for manufacturing, additive manufacturing. So let's look at that, particularly in the context of biomimetics for design for manufacturing. So as you know, biomimetics is mimicking nature, okay, learning from natural systems, and in order to have engineering applications by learning from that. So we have parts with complex geometries and so on that are then additively manufactured because that gives you the capability of doing it. So there are different meanings of biomimetics. One is that you take real biological input and try to emulate nature and its unique properties. Second is that you use cellular or lattice structures and repeat them in order to create designs for various applications. Third is you incorporate multiple functionality. And fourth is that you consolidate numerous parts together into one and thereby reduce waste and get other advantages. And all of these, there are 3 broad biometric principles. One, and I'm going to repeat, these are the 3. One is you customize, create customizable freeform surfaces. And second is that you use something like a biological evolution process. simulation-driven design in order to make what is called topology optimized or generative design parts, and the third is lattice designs. So, all of them can be or may not be used with the biological input as inspiration. So here is an example of where biological input is used. This is a helmet with enhanced safety. So you take lattice structures that are directly inspired from nature, in this case resembling honeycombs, and you put it together in order to design highly efficient material only where needed and not where it is not needed, and optimizing the weight of the final part. In this case, it's a helmet for the American football as a protective environment, equipment, and and you get these bike helmets. First of all, bike helmets which are lighter, stronger, more comfortable, more personalized, leading to apparently 26% safer helmets than otherwise. It's a lighter one, it's also safer. And in the context of American football, they apparently have this force of impact up to 7% reduced when the head hits the ground directly. That's a very impressive performance. Let me spend a little bit of time with one more example, and something again very surprising, and this just came this month in the journal, that creating cement-based super hydrophobic metamaterials. So basically, cements that are extremely afraid of water. And of course, there are many natural materials. They have unique properties. Cement, of course, is one of the most used, probably the most used material in engineering applications, because of the number of buildings and other structures that you make using it for very good reasons. But they also have problems, right? They also have porosity, micro cracks, poor plastic deformation, and so on. So they need improvement. So the question is, can we learn from nature, redesign them, that have superior thermal, mechanical, durability, and sustainable properties by learning from nature? For instance, there are lamellar structures that are there in naked layers. Okay, so they are brittle if you take each individual element, but put it together, they are not brittle. Right? So can we use that for both high strength and high toughness? Normally you wouldn't associate them with each other. Okay. Similarly, cuttlefish bone, lightweight porous structure that gives high impact absorption and also thermal insulation. Or something like a lotus leaf which has got hierarchical surface roughness and hydrophobic wax coating that gives you this super hydrophobicity. So using just the last one, lot of work has happened in the last few years, leading to a whole bunch of strategies for creating super hydrophobic cements. Okay, and I just enlisted some of those there. I think the details are right now not important. Important is that these are the kind of works that are happening, and it can dramatically transform the properties of things that we take for granted. A will happen when B will happen. Not necessarily. If you look at ISpA chart, right, where you can put different parameters of material, okay, against each other and see how the materials perform against those parameters, there are certain areas that are covered by materials, other areas that are not. We can fill those areas by creating metamaterial. For example, negative Poisson's ratio, right? Negative refractive index, and so on. There are materials that have been developed in those. And more recently, you can channel heat at perpendicularly now in a material using, again, metamaterials that are inspired by nature. So that's one example. And these are just few examples of hydrophobic materials: lotus leaves, rice leaves, mosquito eye, I didn't know that, cicada wings, water strider, of course it can move on water, gecko paw, and rose petals. Just some examples. Rose petals you knew, we saw these beautiful pictures. And the materials and the strategy that biology uses is somewhat different from each other. But you can learn from that. Now there are of course challenges with everything, in this case as well. Quality issues are there, all kinds of quality issues, you can read them. One of them is material getting stuck inside. You can't take it out. Right? And if you look at this design here, I'm not sure that you can see but probably we can. Anyway, there are areas where the dust is inside. The pores are filled with things and they are nowhere coming out. So these kind of things can happen. Okay, there is a limitation on what is the minimum size of thing that you can print and what's the maximum size of thing that you can print. Build angles are a major thing. The moment you have a downward angle, you have a problem. You need more support structures and so on, and the quality on the top and the bottom are different from each other. Support removal, as I said, is not a easy process. Top right example. Latticing is often not part of the topology optimization. So you do a uniform topology optimization and then say, okay, I'm going to use this lattice now to replace those parts. But more recent work, and this is very encouraging, is looking at doing both of them at the same time. So optimization of repeated lattices. So what you do is you do the variation in the kind of lattice that you will use, and also the relative sizes of the components within the lattice. So in other words, we as engineers have largely taken it for granted that there will be homogeneity inside the structure. Now is an opportunity for us to embrace inhomogeneity. I think then I'll skip that. Size related challenges, okay, as I said, you can't be very big, but they are, at the moment, we are making very small parts using very large machines. And that's not a great design, okay? We need to be able to think of little human beings like me, building skyscrapers. Why is it that for additive manufacturing, we get a machine of this size and make a big part, ours is 100 by 100 by 150, or 300 or 400 millimeter things. I mean, that's not good design. I think we need to work on that. And I think one area that is expanding very rapidly is using robotics in more clever ways that can go around and build bigger things. Okay, quality versus size is another issue. I will skip that. The importance of Industry 4.0 again in tracking. Just we need to understand it the least better. Okay, so there is a very interesting article on the pros and cons of gantry versus robotics, and you see that gantry is faster build speed, but then robotics has greater mobility. So again, question is how do you bring both into the machine rather than one or the other? Okay, and that's multiple challenges there as well. So that's what I was alluding to. Can we get inspiration from other activities, construction of building ships, parallel modular construction, bringing it together is something that is worth looking at. Okay, and these are some of the productivity challenges. So I will skip that. Role of post-processing, which brings it down, and parallel manufacturing without increasing cost. Okay, training is a very important area, right? Difficult to find trained personnel. There is a very interesting program at ISpA called Digital Manufacturing Smart Factories program that trains about 100 people every year, professionals, okay, in all aspects of Industry 4.0. And they have, by and large, they are getting people of average 15 years of experience. Okay, but it's not open only for people of that kind of experience. Anybody can join. So that's something that I'd like to encourage people to take advantage of. What kind of training? Well, DFM, Metal Aim, and Industry 4.0 are three major areas where we have difficulty finding people. Then maintenance is a big challenge. So again, we need training and support in that area. This is the advanced manufacturing program at ISC, where we do all of that. I think we all do in our own ways. I just want to quickly go into this one. This is the Digital Manufacturing Smart Factories program. You can Google it and you can look at the sort of 360-degree exposure to Industry 4.0 that you can get as a result of that. So around the smart factory, we initiated India's first smart factory research platform in 2014 with a seed funding from Patil company. And that has grown now with funding from Ministry of Heavy Industries into a full-fledged smart factory as of 2019. You can do research to create knowledge, development to create technology, translation to create products and startups, and training to get skilled personnel. So this DMSL program is also being supported by that. That's the smart factory. And the idea is that can you use automation in order to not only replace people but also empower people. Okay, can I take even regular legacy machines and turn them into digitalized machines that are connected in a factory, but people work, but work with data efficiency. So we created two platforms, okay, one with advanced features by way of machines and sensors and so on, so collaborative robots and AGVs and so on and so forth. And the other is just a regular MSME, but it's completely digitalized. People are working, but that data is being used in order to make their performance better. With KPIs such as quality, productivity, resource utilization, safety, and so on being improved. Okay? So two platforms, one is automation intensive, the other is people intensive, and both are connected to each other. And there's just some visuals from that, and the factories and how they are connected to each other. And we've created a lot of impact, at least in that part. Last part that I want to talk about is sustainability. Just a couple of slides on that, because this is a very important area. I think somebody said reduce 3R or RRR, but this is an area that globally actually not as much research. We do not know what kind of impacts. If you create a part with multiple materials that are next to each other, that are glued or pasted to each other, how is it that you are going to recycle them? How are you going to take them apart? This is a major area, but also, what happens when you do additive manufacturing? Do people get other safety hazards associated with it? Some work is going on, but a lot can be done or need to be done. Okay, you can say from a broad thing, net reduction of environmental load compared to conventional machining, and therefore, material energy consumption goes down because it reduces the amount of waste generated. So that's a good thing. But on the other side, you also have this. Some materials used in 3D printing like ABS, PLA or nylon can generate health hazards. So how do you now come up with new 3D printing processes that gives all the good things and takes away the bad things? Right? Similarly, there are extruder temperature, for example, in one study, plays a critical role in particle emissions. And some of these fine particle emissions can be carcinogenic for humans. Right? And similarly, there are other environmental impacts that we need to be aware of, and more research is there. In particular, we know by and large that metals are mostly recyclable, but the way you print will also determine whether they will be or not. So you may not be able to take them apart. Recycle plastic because that the recovery is possible, and then you can reuse it. But primarily the ceramics and so on are pretty much non-researched at the moment. We do not know, so you need to do research on that. So in summary, three major points, and this is something where I'm quoting Professor Suresh, and I talked about it, but I just want to bring it in one place. One is that it's not a panacea. Additive manufacturing is not a panacea. It has its own pros and cons, and we need to identify what those are. Either live with it or try to expand that beyond it. Okay? So that's number one. It's just another manufacturing process. Second is, things need not be made of isotropic and homogeneous materials. Let's take advantage of anisotropy and inhomogeneity the way nature does. The third point is that as engineers, we focus much on the shape exterior, assuming that the material is uniform. Let's look inside. There's so much that can be done. If you look at a bone, it has metastructures, and then structures, then substructures, each of them providing very interesting characteristics. How do we bring that into our design? It's a very important expandable area, so biomimetics is a major area. Designing indigenous machines and critical machine components are absolutely key here, and hybrid manufacturing is a major area of research. Industry 4.0 technologies, connect, sense, process, control, need to be far more ubiquitous in our way of working with the AM in all these aspects. Okay? And sustainability impacts are important to assess and control. And we need training at all levels. All of that is not going to happen just like that. We need people. So that is extremely important. I have consciously left out two major areas. And that doesn't mean that they're not important. They're very important areas. One is aim of composites and the other is aim of construction. That requires a great deal of discussion, that's why I left it out. But please pay attention, they are very important areas. Last, supporting creativity. It's not good enough. I'll just stick to one. So it's not good enough to say, okay, fine, just go and do it. How to be more creative in thinking of radical solutions. Okay, so here's an example, and that is thankfully actually worked out with ISRO. Okay, so this is some of my work actually for the change, how to support design creativity. How can I use databases of existing systems, including biological systems, as stimuli to make people more creative? And then you can transfer that to machines and make machines more creative as well. And here's an example, right? So here is a problem. Sonic boom is a problem, was a problem when Shinkansen, the bullet trains were going through a tunnel, and that produced this shock wave, boom, created, right? So they looked at nature and found out kingfisher that it can very quietly go inside water, because otherwise it will lose all the fish and manage to get the fish, right? So it learned from that and changed the front of the Shinkansen that allows a very gentle, okay, software there. And so what we did was, in ISC, we said, well, if we can understand how something works, including biological systems, then we can use that as inspiration for designers to create very different ideas. And so we created a model of causality, how something works, and then created a tool called ISpA. This was done, it's the world's first computational tool for systematic bio-inspiration that we developed with ISRO for designing novel designs for solar antennas and later on for lunar mobility platforms for Chandrayaan, right? And so you have things like this. That's a Venus flytrap. And how does it work in order to basically get these nutrients from insects? Or this is a friction disk, which is a continuous gearbox. How does it work? And you can use these kind of things, a large number of them, to say, here's my problem. Tell me how nature does it. And it gives you inspiration. And here's a little example of how that can change. Now, here are 3 different designers. And when they worked on their own, they created 9, 6, and 8 problems. These are related to solar antenna designs. And at least 4 or 3 ideas were very good. But then when they ran out of ideas, we gave them idea inspire, and they got stimulated to create it. And of course, there are individual variations among these people. 2 of the designers were extremely inspired, and other one was not. But you see the jump, additional ideas are getting created. That's heavily creative. Okay, and we have done many work on that. Last part is sustainability. How do you support sustainability of a? You can do assessment. So we created a tool where if you have a design like this one, you can go to a database, you pick up the processes that are there in the life cycle of the product, and then you can get estimations done as to how it is going likely to impact the environment. And you can compare different designs using that and choose the best one. And what's the effect? So here is an example. We gave design teams 4 different inputs to 4 different teams. One, we said, well, we want you to design more environmentally friendly products. Find anything from internet and use it. We give them particular literature to help them. We give them commercial software to help them, and you give them ideas sustainable through their development. And you see the final designs, environmental impact estimated, went down from 25.7 to 1.1. For one example, you can see that because of that example. So it changed systematically the problem and the input combination. Here is for the second problem, okay? Here is for the third problem, and here is for the fourth problem. So on average, there is a 25 times reduction in environmental impact as a result of doing this kind of design. When you are helped, the designer is helped. So they explore more ideas, more or less the same, and still manage to get much lower environmental impact. That's exactly what we want. And that brings me to the last slide. Really, my last slide. Okay? And when you see, okay, this is really in conclusion that this is an example of a design for manufacture, anti-manufacture part where a part was made 40% lighter by DFM. So what this particular study did was, it looked at if the, okay, so there is a 54% cost reduction due to 40% material savings through design, and how does it happen? One is that the amount of material is less. So whatever the cost of that, you multiply by that and that goes down, right? Second is that build time has become less because you have to build less the machine cost is less because the usage time is less. And the fourth is pre and post processing cost is less because there is less amount of things to pre-pro or post-process. And if you put all of this together, there is a dramatic impact of 54.2% reduction. Whereas if you made the speed twice as big, you didn't get that much difference. If you made the feedstock far less cheaper, you didn't get that much. So this has a knock-on effect on every stage of the cost. Therefore, again, design for additive manufacturing is the critical area. And that's the last slide. I'm just acknowledging my colleagues here. Okay, Manish Arora, Gurumurthy, Viswanathan, Anand Suresh, Satyam Suvas, Sai Shivagoji, and a whole bunch of other people that I haven't spoken about. And that will be excused. End of the talk. Thank you.
So that's very, very comprehensive overview of the additive manufacturing. Yes, not everything. I don't want to repeat or give a summary of that. But a few things I think our organizers, when they come up for the recommendations for the future, that probably will be useful. One of them is that what he mentioned, when we are talking of machines for manufacturing, additive manufacturing, many things are still imported. And it's really surprising that things like controller, we are supposed to be so good in electronics. But the controller, whether you are for UAV or whether for additive manufacturing, very important. So these are the very simple things can be done. But why we are importing? Maybe because we have not put the mechanism to do those controllers together. Similarly, when he talks about some of the other issues, components in the additive manufacturing, the real issues are that we have not addressed that issue in a comprehensive way, and we expect that some small company or big company in India will do that. So maybe a focused approach is required with respect to additive manufacturing. What are the gap areas? I was also thinking maybe perhaps request our INAE coordinators to see whether they can recommend. There are many types of, you can say, organizations or societies, whether it's a metal or whether it's a welding, but we don't have anything of that type on additive manufacturing. A body, you can call it society, you call it association, whatever you call it, it should really take the overall view, because additive manufacturing is the future of tomorrow manufacturing. So how do we address that as a country that will become a leader? So there has to be some kind of a group which really should address it, maybe annually meet or 6 months meet, something like that we have to do. Again, I would like to thank Professor Andre for a very, very comprehensive view, and big applause to him for this.
Thank you, sir, for that passionate talk on the challenges in additive manufacturing. I request the session chair, Dr. P.S. Goyal, to honor our speaker, Professor Amresh Chakrabarty, with a memento. A big round of applause for the speaker of the Plenary Talk 2, Professor Amresh Chakrabarty. I request Dr. Darshat Ram, former Director DRDL, Distinguished Scientist, Local Organizer Committee Chairman INAE, to present a memento to our session chair, Dr. P.S. Goyal. We are very thankful for your valuable presence today, sir.